Alright, ladies and gentlemen, we have our linear programming problem. This is the example we started in class, and I told you I would get a video for you to work through the entire example so you could understand the thought processes we need to use when we are trying to solve a linear programming problem. Now, like any good word problem, we're going to start by reading it. So let's check out what we have. We've got Yum's Bakery bakes 2 breads, type A and type B. One batch of bread A uses 5 pounds of oats and 3 pounds of flour. One batch of B uses 2 pounds of oats and 3 pounds of flour. The company has 180 pounds of oats and 135 pounds of flour available. Write the constraints for the problem and graph the feasible region. So the next thought process we need to take is, what is this question asking me? What is this problem presenting me with? Well, my keywords are constraints and feasible regions. If I'm developing constraints and feasible regions, I need to find inequalities, because inequalities define the constraints that help me identify my feasible region. After I graph those inequalities and I see where they all overlap, where all the shading overlaps, that defines my feasible region. So when I'm looking at this problem, if I'm doing inequalities and constraints and feasible regions, we're working on a linear programming problem here. Obviously, I'm limited by something. I have these constraints. I need to define or find the item or items that are constraining me. Not necessarily the equation yet. Let's just try to see if we can see what is constraining me. What factor is my limiting factor? Here I have 2 types of bread. Not really limiting me at all. It's just 2 types of bread. Batch A, one batch of bread A uses 5 pounds of oats and 3 pounds of flour. So while these are rates, 5 pounds of oats per batch A and 3 pounds of flour per batch A, it's not really limiting me at this point. It's just telling me how many pounds of oats I need and how many pounds of flour I need to make one batch of bread A. And the same thing with the batch of bread B information. I need 2 pounds of oats for a batch, and I need 3 pounds of flour for a batch. But this next sentence, ladies and gentlemen, the company has 180 pounds of oats and 135 pounds of flour. We could read that statement as well as the company only have 180 pounds of oats and 135 pounds of flour available. So what is limiting me here is the availability of oats and flour. So now I've got my limiting factor here. My limiting factor is oats and flour. These are the things, the real world items that are limiting me. So let's see if we can develop now. Let's see if we can define the variables that we're going to use here. What are my unknowns here? Well, I know that it takes 5 pounds of oats and 3 pounds of flour for a batch of bread A. I know that it takes 2 pounds of oats and 3 pounds of flour for a batch of bread B. And I know that I only have 180 pounds of oats and 135 pounds of flour available. I don't need to use a variable for things that I know. What do I not know? I don't know currently this fact right here. I know I have 2 types of bread. I have a type A and I have a type B. But I need to come up with 2 variables to identify the unknowns. I couldn't say that one variable is A and one variable is B in this case. I couldn't say X equals A and Y equals B, because A is just a type of bread. I'm curious. I need to figure out how many batches of bread A I'm going to make. I need to find the quantity or the number of batches of bread A, and I also need to find the number of batches of bread B. My variables then can be X will be the unknown value that represents the number of batches of bread A. Y will be the unknown value or the variable that represents the number of batches of bread B. So here I've got X batches of A y batches of bread B. Not a very good y there. Let's make that y look a little nicer. I have y batches of bread B. And now we need to figure out what are the rates then. What rates can I use? If I have variables, sometimes I have to put coefficients to them. And in real world scenarios, these would be the rates that are affecting each of these variables. So what rates do I have for the number of batches of bread A? Well, I know I need 5 pounds of oats per batch of bread A. I know I need 5 pounds of oats per batch of bread A. And let's look at the batch of bread B. How many pounds of oats do I need there? I need 2 pounds of oats per a batch of bread B. I've got another element out here I need to worry about, my flour. I need 3 pounds of flour per batch of bread A, and I also need 3 pounds of flour per batch of bread B. And now I need to relate these items to what I have available, to my limiting factors. My limiting factors here, what I have available, I'm limited to 180 pounds of oats, and I'm limited to 135 pounds of flour. Now I've successfully identified my variables, the things that I don't know, as the number of batches I'm making of each kind of bread. X is the number of batches of A, Y is the number of batches of B. I see my rates in here. 5 pounds of oats per A, 3 pounds of flour per A, 2 pounds of oats per batch of B, 3 pounds of flour per batch of B. And I know what my total values can't exceed. I'm limited to 180 pounds of oats, 135 pounds of flour. Now, it's an easy process to transform this little table we've made into our inequalities, into our two inequalities. The first line, if we read it, I have 5 oats per batch of bread A, which is X, plus 2 pounds of oats per batch of bread B, or Y, because Y is my number of batches of bread B, and they cannot exceed, or they must be less than or equal to, rather, 180 pounds of oats that I have available. So I only have 180 pounds of oats available. The total pounds of oats that I use must be less than or equal to my total available. In a similar process for the flour, I need 3 pounds of flour per batch of bread A, 3 pounds of flour per batch of bread B, and that total needs to be less than or equal to my available amount, which is 135 pounds of flour. So again, we have our rate of 3 per number of batches, 3 per number of batches. And in this real world scenario, we need to apply a little bit of thinking and common sense. I'll never have a negative batch. I will never have a negative batch, so my X, my number of batches of A, will always have to be greater than or equal to 0. I could make 0 batches of A, but I could never make a negative 1 batch of A. And similarly, I'm going to go ahead and throw a gray value in here so we have a third line color. My batches of bread B could be 0, but it could never be negative a number. So my Y will make gray so we can graph it easier. Now I've got everything in this problem represented. I've taken all of my constraints into consideration and developed my constraints or my inequalities. Now I can use these to graph my feasible region. So how might I graph the feasible region? Well, there's a couple different ways we can graph linear functions. We know they're all linear because there are no exponents greater than 1 out here on any of these variables. So I can rewrite these two, my oats and my flour inequality, or my oats and flour constraint, I could rewrite them into a slope-intercept type form. So to graph an inequality, I'm going to treat it kind of like a line. So I'm going to put it into the slope-intercept form, still respecting my inequality symbols when I do that. So I could figure out where my y-intercept is, and then I could use my slope to graph it. We could make a table of values. We could find our x and y intercepts, and that might be quicker at this point, but I think the slope and having it written in slope-intercept form is going to be valuable, so let's go through it that way. So here I can rewrite my Oates inequality and begin to solve it. First I get 2y is less than or equal to negative 5x plus 180. I bring that 5x to the other side, and I divide both sides by 2. Y is less than or equal to negative 5 halves x plus 90, because 180 divided by 2 is 90. I'll go ahead and box that, because here I've isolated my y. I've got my inequality in a slope-intercept kind of form. And now let's move on. We'll do the second one. We have 3x plus 3y is less than or equal to 135. I need to move that 3x over, so 3y is less than or equal to negative 3x plus 135. Divide both by 3, and I get negative x is, or excuse me, y is less than or equal to negative x, and 135 divided by 3 is 45. And I'll box that one up so I can find it easily when I'm graphing. And let's go ahead and graph our simple ones first. X is greater than or equal to 0. Well, that's a vertical boundary line right here. Trying to make sure my lines are really straight here. A little difficult with this tablet. X is greater than, and so x is greater than to the right, it increases to the right, so this boundary line shades to the right. I'll just use an arrow for now so I don't get too messy of a graph. My y greater than or equal to 0, that's a horizontal boundary line, and I'm solid on all of these because it's greater than or less than or equal to. So that equal to makes sure that I don't need to do dashes. And y is greater than or equal to above the line, so I need to shade above the line. Let's look at our Oates equation. My y-intercept is 90. Here my y-intercept is 45. So we probably don't want to use a scale of 1. Let's go ahead and define our scale by 10. So this would be 10, and then 20, 30, then 40, then 50, then 60, then 70, then 80, and here's my 90 line. We'll do the same thing down here, 20, 40, 60, 80. So my y-intercept is 90 on my Oates equation. We'll put our y-intercept there, and because my scales are the same, my x and y scales are the same, I can apply my slope as it's written. So I go down 5, 1, 2, 3, 4, 5, and 2 over. Then I go down 5, I'm going to go below here, but that's alright, and 2 over, be right around here. Make this a little brighter green there, and I need to connect these lines as straight as I can. Not very straight, I see. Let's try that one more time. Let's see if I can get it a little more accurate. I could also say my slope is negative 2.5. So I go down 1, 2.5, and I go over 1. I'll just plot a couple more points here. 1, 2.5, go over 1. There's that point. And 1, 2.5, and I go over 1. Here's this point, and then now I have decent enough points to try to get a little bit of a straighter line so that my graph is not quite so messy. There we go. And this is going to be less than or equal to, I'm going down. Now let's graph our Oates inequality. Y is less than or equal to negative x plus 45. 45 is my y-intercept. So I'll graph my y-intercept here, and I'm negative x, so my slope, I'm going to go down 1 over 1, down 1 over 1, down 1 over 1. Look at that. Down 1 over 1. And I will connect my lines. There's an intersection. That'll be important in a minute. There's an intersection right here. If I drew my line beautiful and straight. Give it one more shot. You guys know that I am not the best at drawing straight lines. There, that's a little better. Alright. And this is less than or equal to, so I will shade here. Now if I look at my feasible regions, they intersect in a lot of places, but if I look at where the shading would intersect, my red equation would go this way, my gray is coming up, my green is going down, and my blue is going down. So here I have my feasible region right in here. Almost a triangle, but this little intersection here makes it not a triangle. My feasible region is in here. Now, after I have written my constraints as inequalities, I've graphed them. I've done that now. We have our feasible region defined. I need to look at the vertices. I need to find my vertices. And we need to do that because, as we mentioned in class, if I have a feasible region, I can come up with an objective function, which we'll talk about in a minute. And that objective function, the maximum and minimum values, will be found at these change points, or these vertices of my feasible region. So I want to make sure that I identify them now, so I know what points I need to test in just a minute. So my vertices, let's just identify them, is my y-intercept for the flower equation, and that one was at 0.45. Let's go down here really quick. I've got a 0, 0. That's an easy one to start with. So let's start with a vertex at 0, 0. Between the x greater than 0 and my y greater than 0, my intersection of the feasible region is 0, 0. Here's another stopping point for the feasible region, and this point is 0.45. I'm just going to record my vertices down here in my nice little table. Moving along, we have another vertex here at, this is the 30 line, 30, and when this is 30, when x is 30, both of these equations, my oats and my flour equations, equal 15. You guys can check my math if you'd like. Just plug in 30 for x on both of these, and you'll get 15 out of it. And then here we have the vertex when my y value is 0. When my y value is 0 on my oats line, that would mean 5x is less than or equal to 180. So I want to double check this. When my y is 0, my vertex here is on my oats line. When y equals 0, I get 5x less than 180. And when I divide both sides by 5, I get 5x is less than or equal to 30. What is that? 36. That would be 180 divided by 5. 30 would give me 150, and then 6 would come up the last 30. So you guys can double check my math again. 180 divided by 5 is 36. So my final, oops, change my color back. My final vertice is going to be 36, 0. Now again, remember that my x and y axis and my vertices, it all goes back to the variables that I defined initially. My x represents the number of batches of A, so here I'm saying 0 batches of A and 0 batches of B. And here I'm saying 0 batches of A and 45 batches of B, and so on and so forth. Now we have successfully, get that out of the way so we can read this next part, we have successfully graphed our feasible region, and now we have determined our vertices. Now we need to start looking at the next part of the problem to figure out what is the object here. We have our constraints identified, but what are we being constrained from? Well, Yum's Bakery wants to maximize its profits. Like any good business, it wants to make the most money possible. We want to maximize our profits. Then we want to maximize our profits from the bread sales. One batch of bread A yields a profit of 40. And what do we define one batch of A as? We've already defined one batch of A as our X value up here, right? So my objective function is going to be about profit. One batch of bread A yields $40, and one batch of bread B yields $30. So use this information to find how many batches of each bread the bakery should make. Well, we're trying to maximize our profit. So we could make an equation where profit is represented by, well, the amount they make for each the amount they pull in total, right? Well, how much profit do they get for bread A? For every batch of bread A, they get $40 worth of profit. $40 of profit per batch. 40 is my rate. X is my number of batches. 40x is the total profit from the batches of bread A. We want to add that to the total profit for the batches of bread B. They make $30 in profit per batch of bread B. And again, I've already defined these variables. I'm using these same variables. X is the number of batches of bread A. Y is the number of batches of bread B. Now I have the function that tells me what the profit is. And I'm not looking for an inequality here. I'm not looking for the feasible region that I could use or the possible answers I can get out of here. I want to know what is the largest answer I can get out of here. When I look back at this graph, it becomes very difficult because there's so many possible combinations given my constraints. If I didn't have any constraints, I could just make these x and y values as large as I wanted to and make this p value go up to an unending or an infinite number of numbers that increase and never stop. But I need to evaluate this profit function given the constraints that I have identified up in the first part of the problem. So again, with the vertex principle, we know that the maximum or the minimum value for this function will come from one of these vertices. If I need to find the maximum profit, now I need to use my function, my objective function, to analyze my different vertices, to look at the different combinations of batch A and batch B that I have here for my vertices and try to get the top number value. Well, let's look, and I'll write the equation out of here. Normally you'd write this equation into here, but it's not much space. I don't know if I'll fit it in there. I'll try on the first one and see if I can make it. I would say 40. Here my number of batches of A will be 0 plus 30, and here my number of batches of B will be 0. And what's 40 times 0 plus 30 times 0? Obviously, I'm making no profit if I make no batches of bread. That's not the one I want to go with. So this vertex, this combination is not what I want to go with. Let's check the next one. And we'll do the same thing all the way down. 40 times, if I make no batches of bread A, then given my constraints, I can make a total of 30 times 45 batches of bread B. Well, what is 30 times 45? 30 times 45. Got my little calculator off screen here to make sure that I'm not messing you guys up. 30 times 45 is 1,350. So I've got $1,350 in profit for this combination. Let's check our next combination out. I've got $40 times 30 batches of bread A plus $30 of profit for 15 batches of bread B, and 30 times 40 is 1,200, and 30 times 15 is 450. So that gives me a total of $1,650. $1,650 total profit for this combination. Now let's see if we made as much batch A as we could, and we didn't make any of batch B. I would just get 40 times 36 plus 30 times 0. We all know that's 0. But what is 40 times 36? Well, that's only 1440. So in these values, we will get from these vertices, one of these vertices will give us our minimum value. And here it is. Our minimum value is if we make no batches of anything, we end up with $0 profit, which makes sense. We didn't sell anything. And then this vertex, I get a 1350, and I get a 1440, and then I get a 1650. Well, the vertices don't necessarily, we're not guaranteed that each vertex will give us a max or min. We are guaranteed that within all of these vertices, one will give us a max and one will give us a min. Here's my minimum, and my maximum then is $1,650. So the answer to this, the way for the Yum's Bakery Company to make the largest profit, the way to maximize my objective function, I need to have 36 equals x, and I'm sorry, writing the wrong one. Go up one level here. I need to have this level here as my solution. So I end up with x needs to equal 30 and y needs to equal 15. If I pair that back into my actual meaning, I need to have 30 needs to equal the number of batches of bread A, and 15 needs to equal the number of batches of bread B. So ladies and gentlemen, this is my final solution. The way to maximize this objective function, the profit function we defined, given the constraints that we have based on the flour and oats, I would want to make 30 batches of bread A and 15 batches of bread B, and I will make a profit of $1,650.